Welcome back, chat. Today's lesson's gonna slap, no cap. All right. God, he's cool. He's so cool. All right. So, yeah, Kendrick Holloway. That's what the K is actually for. Sweet. All right. So we got some layers of our atmosphere, right? There's 4 layers, 3 boundaries. We have the troposphere, low. This is the one that we care the most about because it's where weather happens. Okay, stratosphere. Higher up, still important because it has a lot of O3 or ozone, which protects us from super skin cancer. We get the mesosphere. The O3 is gone. Temps start to fall again. It just kind of hangs out there. It's fairly large. Thermosphere, we start to heat up a little bit again. There's a little bit more oxygen up there. And then finally, anything beyond this, realistically, we are looking at essentially space. The space station is only like 400 kilometers. So it's low Earth orbit. It is still in our atmosphere, but it's not in enough atmosphere that it has to like drag through it. Yes, ma'am.
If we were to go to the mesosphere, you'd get the sun would hurt you, but you'd freeze.
You would freeze before you died of radiation, yes.
But it both would.
I mean, realistically, you'd probably, I don't know if you would suffocate just because there's not enough oxygen to breathe,
You could
or
just be there, like,
you would not live is the important part there.
But
Yep.
would the sun get you?
I mean, the sun will get you everywhere.
Say we don't freeze to death.
You will get terrible skin cancer and skin burns. Absolutely. Okay, so here we are. Heating the atmosphere is where we left off. And we looked at this picture where we have just 2 different versions of the Earth. It has a pretty pronounced tilt, right? So 23.5 degrees. And all that we see is summer and winter based on this picture. Is this picture to scale? Not even a little bit, right? The sun is way, way bigger than our planet. Now, as we look at this, there are some other pieces that we're going to zoom in on this picture because certainly this has something to do with it. The equator, anybody who's ever spent much time there, is there really much of a difference between winter and summer on the equator? Like, in fact, it really doesn't even make sense to talk about summer and winter at the equator because essentially what winds up happening is you either get rainy season or you get hot season. Like, those are the 2 options. Now, when we look at it, there is a difference. So like summer here, why is this summer? Like right here, why is it summer in the southern hemisphere? So it's tilted closer to the sun. In reality, does that make a huge, like noticeable difference in the actual scale of our universe? Like you want to say closer to the sun makes you hot, right? But the last class I believe that we talked about when you climb a mountain, it gets cold and you're way closer to the sun at that point in time. So the actual distinction here, the tilt certainly plays a role, but it's not so much about the distance that you are from the sun. There's something else going on. Now, to draw this to scale, and I would not suggest it, but we're going to look at this a little bit closer. I know that the tilt of our planet has something to do with it. Okay, if we were to draw this to scale, and I'm just guessing here, do not draw this as big. Say this is a part of the sun. Like it's huge. That's part of a circle. Our Earth, I don't think we'd even see it at this scale. Our Earth would realistically probably be like over here or maybe at Cache. It's really far away. Really, really far. Which means it would only be like that big from that distance. It's crazy how small our planet is compared to the sun. Now, we're going to work with not a scale model because we just don't have time to draw it. But what we will do is we'll look a little bit closer and we'll just say, gosh, what about those rays of sunshine? What about the light that hits? That's what I'm really focusing on. Okay. Now, this is a weird idea when you see it not drawn to scale, but we're just not going to draw the sun. Okay. Let's say, and I'll zoom back in, that we have planet Earth hanging out here. So here's a lovely planet Earth. And we can tilt it if we want to. That's fine. We'll say it's tilted there. And here's our equator. All right. Step 1. Can't stress this enough. The sun compared to us is what? Huge. So realistically, if I could see the sun, I don't think my one just now did it justice. This is what the curve of the sun would look like if we compared it to Earth. Like almost straight, right? Which means if I imagine that there's a sun shining over here, rays of light do this. And it doesn't feel natural for this to be the case, but because the sun is so large, all these rays of light that strike our planet are essentially parallel. They don't really come in at angles because the sun is too big. It's all coming just from this one little section of the sun. They're all parallel. Now, if you went through here, let's just think about what happens with light. Anybody ever been driving down the road and the person in your passenger seat is playing on their phone and you just get blinded? Because light does what off their phone? It just reflects and it bounces, right? So what I want you guys to do, I'm going to give you a second. I want you to take this picture and go one step further. Show me what you think this light is going to do if we just assume the Earth was like a mirror. We'll pretend it is right now. Which way would the light go if the Earth were a big mirror? I want you, this is not the right answer, but what I'm looking for is if you do this and say, oh, it shoots straight down. That's okay. I don't think that's what's going to happen at that point. You guys reason it out. I want to see what you come up with. I'm going to give you like a minute. Draw the picture. You don't even have to be perfect. A circle with these parallel rays of light striking the Earth. Show me how you think the light deflects. So as I'm going around looking at stuff, few people have the right ideas. Quick check. How many of you guys have played pool before? Or seen a pool table and watched somebody hit a pool ball at least one time? Okay. Pretend that we're way zoomed in. And we don't have to, you don't have to draw this, but that's still curved. If we zoom in far enough, the Earth looks flat, right? Okay. If I shoot a pool ball and I strike it right there, you tell me when it stops. Is it going to shoot straight back where it came? No. Where do you think it's going to stop? Right about there. I agree with you. If you hit it perfectly, this angle is going to be the same as this angle. Okay, a little bit of geometry. Now, the same idea winds up applying to this. And I'm not super worried about the physics of how does light reflect off of a globe or a sphere. Like, that's not the main part here, other than we're going to be able to relate it to something that we know. This light strikes at a pretty big angle. This angle right here is fairly large. Would you agree? Like, it's super obtuse, I think. Now, as I'm looking at this, I think the light's going to come off about like this from that one. Now, in reality, does all of the light that hits our planet reflect? Does some of it? And at better, can you guys all see me right now? Because what's bouncing off of me? Light is bouncing off of me and straight into your eyeballs. Okay, with that, some of the light absorbed into me though. If you've ever been outside in the summertime wearing a black shirt and felt hot, you know that this happens. Okay, here, what's going to happen? You guys tell me when to stop. I'll start down here. Okay, I'm going to go back to about here. I think roughly there. And I'm just looking what I'm deciding to do this. And this isn't perfect because we're not doing the math. But it's roughly perpendicular is how it's going to shoot off. Okay, how about here? It's kind of hard to tell. It's almost straight back, right? Okay, now last one. Which way is this going to deflect? It's going to go downward to some degree. Maybe it's like this. Depends on how it hits, right? Here is a really important part. The tilt of our planet certainly has some amount of how close to the sun are we. That's part of it. In this picture, is it winter or summer up here? It's summer up here because I see the lights coming over and it's striking the planet. The smaller the angle, the closer to perpendicular that you hit the planet, the more energy that can be absorbed by the planet when it strikes. When we just barely glance off at the poles, so like here, it's winter there, but it just barely touches and bounces off. Very little energy is being transferred to the planet through that light at this point. We're going to just make a note, no matter what time of year it is, around this area, they're going to be essentially just straight back out, which means they're going to hit as flat as possible against the planet. This is where you're going to get the most energy absorbed, and it just happens to be where on our planet? The equator. And what would you notice about the weather of the equator, like pretty constantly? Winter or summer, what's the temperature? Hot, because the way that the light strikes these. It doesn't matter there because they're going to get the same angle pretty much all year round. So, really quick, easy thing to kind of knock out here. There are a few different pieces that kind of fit into here. We're going to make one easy summative statement. The angle that light hits Earth plays a huge role. Now, just so we can see, we're talking about huge role in what? If we go up, heating. There we go. In heating our planet. Now, the most energy is absorbed when we're pretty close to perpendicular. Or in 3 dimensions, you would truly use the word orthogonal, but that's okay. Now, this idea, when we represent this section that I just circled, it's near the equator, right? What do we call them? If you go to vacation somewhere near the equator, you're probably going somewhere snowy? What's the word that we use for those hot temperatures, maybe nice beaches? Tropical. Okay. If you were to look at a globe, and I don't know how close you guys have you ever seen the word tropic show up anywhere on your globes? So Tropicana, maybe on your orange juice. Oh my, Tropic of Capricorn and Tropic of Cancer. So it turns out that those marks, and we're not going to draw a perfect globe, but if we hit these, everywhere in here is where the sun's going to hit the most direct throughout the whole year. So last little follow-up. Pretty much, as we're looking at this, there are 47 degrees where it's pretty nice all the time. 47 degrees on Earth. And we'll say in latitude, known as the tropics. Okay. Now, this is centered around the equator. What's half of 47? 23.5. Now, what this means, if there's 47 degrees near the equator, there's 23.5 degrees north of the equator and 23.5 degrees south of the equator where this nice tropical region exists on our planet. Up north, if you want this is the Tropic of Cancer. And I don't know exactly where these come from, but I have a pretty good guess. Tropic of Capricorn. Anybody in here super into astrology? Okay. I don't know anything about astrology other than I recognize both of those are astrological symbols. I would put money on how clearly the constellation Cancer is from this point and how clearly you can see the constellation of Capricorn. Something to do with how we can see it. Okay. Dwayne and Jarlos, you guys added something more to this, and I liked your ideas. You were talking about something else. So the atmosphere clearly interacts with this. This picture is not real, right? Like, obviously, it's just a picture. But there's more stuff that happens. Now, depending on how you were taught this in the first place, I have no idea. Is it my job to convince you to change your political beliefs at all? Not even a little bit. Did anybody here know my political beliefs? Do you want to? Too bad. I'm not going to tell you. Not a chance. Anybody know what religion I follow? Good. You don't deserve to know. There's no need for you to know. I want you all to think about these as, your own point of view, right? Shouldn't buy into what I'm just telling you. Okay. Looking at this, inevitably there's something controversial coming up right off the bat. Your idea that you were talking about, the heat bouncing off, that has another name. It's called reflecting. I agree with that. Okay. There's gases in our atmosphere that do this. What's this room out here, and why is it warmer than our classroom? That's a greenhouse. Okay. So, as we're looking at this, I'm going to address just the elephant in the room if anybody's offended or disagrees with any of this. The greenhouse effect is not an opinion. The greenhouse effect is real. It does happen. Where there's controversy with this idea is what are the causes of climate change, right? I'm not going to tell you I know the cause. I have no idea what the cause is. I have my beliefs. I know what the science says, but I'm not going to try to convince you one way or the other. I don't care. All I care is the fact that there are greenhouse gases and what they do. So, as we're looking at this, in reality, I'm going to draw one more. There are greenhouse effects and it's caused by certain gases. So, if I ask what a greenhouse gas is, not specifically asking what actual gases do this, when we use the language greenhouse gas, what does it mean when we talk about it? What makes a gas a greenhouse gas as opposed to not a greenhouse gas? Chat it out. I don't care right or wrong. I just want answers. It's awesome. Yeah, I can do that. Why do we call some gases greenhouse gases? That's the question at hand. Why do we call gases greenhouse gases? What about it?
And then they go in and agree. They all like meet up.
Okay, so there's something about the sun. Thoughts?
Yeah, the greenhouse.
Your house is yellow, right?
What is that? Your house is brown, right?
It's not brown. Something white.
Oh, okay.
Yours is yellow, right?
Yours was white though.
That was really fun.
Yellow, shoot.
Like real, all the gas.
Your outside, your outside, yeah, the inside.
My house yellow.
So,
It's like the paint's interior.
It's brown.
No, it's not.
but why do we call them greenhouse gases?
I believe.
You guys all agree that it's probably hotter out there than it is in here? So I'll tell you, it is hotter out there, but there's also ventilation and stuff in this. Why would it be hotter out there? What's able to pass through the windows? The sun, right? Okay, so the sun is hot, but the sun, why doesn't all the sun just bounce right back out? Like, it's kind of a weird question, right? Like, obviously some of the sunlight does go back out. Now, there's these connections between energy and the types of energy that we look at that make a huge distinguishing thing. Do you actually feel light hitting you? Now, that question in general, do you know what light is? Okay, what's light? Not where does light come from. What's light?
A beam of red energy waves.
So I like some of the words. It's a hard question. Okay, turns out that the same stuff coming out of this is the same thing that shoots out of an X-ray machine. 100% exactly the same, no different. They're all just different variations of electromagnetic radiation. You guys remember learning Roy G. Biv? Pretty sure I taught you Roy G. Biv this year when we talked about how far light goes into the ocean. What's Roy G. Biv?
Red.
The rainbow.
They're the colors of the rainbow. Red, orange, yellow, green, blue, indigo, and violet, right? Okay, now, check this out. And I don't even check this out. I want you guys to see this. Do you think you could feel light hitting you?
You can.
You think so?
I can feel
Do me a favor real quick. Close your eyes.
Oh my gosh.
All right, I have a flashlight. Without opening your eyes, Casey, am I shining light on you? Did you just cover your ears when I asked you? Okay. Am I shining light on you?
No.
Are you sure?
Yeah.
How sure?
She can't feel it.
97%.
100, oh, that's pretty close to 100, right? Open
Yes.
yours.
Oh.
Gosh, you don't feel it. I was pointing away first. I was going to change it no matter what. Stonewall, am I pointing light at you? Why do you think that?
Because I can see it.
He's trying to get my freaking eyes. That's why.
Okay. I'm not anymore. Now, depending on how thick your eyelids are, some of you might be able
JB,
to
it's
tell,
over, right?
JB, are you getting him with light right now? Am I pointing light at you? Open up. Okay. Now, obviously,
I only have one left.
you can't really tell, right? Now, there's a reason for that. This is not our focus, but I think it's interesting. Light travels, radiation, electromagnetic, whatever it is, it travels in these things called photons.
Yes.
Photons have no mass. There's no mass to them. They do carry energy though. So there's a bunch of little things shooting at you, but I don't feel it, right? Now, if you have enough of them, you do get a little bit of momentum, like you could make big sails in space, just like old sail ships use. They catch sunlight to move you forward because they have momentum. They do not have mass though. Okay, things get weird when you start looking at that level. However, you can't feel light hitting you. Hypothetically, if I said, let's do this again, but now we're at the equator and it's 100 degrees Fahrenheit and you're all wearing black clothes, would you be able to tell when the light hits you then, do you think? Like, you can tell if you're in the shade or not in the shade, right? It's not the light that you're feeling. What is it? It's the heat. It's the heat generated by that light. So as we look at this, when we talk about the greenhouse effect, windows do a really good job of letting light through. Do we all agree? Can heat get through windows as easily? Can it? If I had a fire burning on the other side of this, I'd be warm.
Yeah.
So let me rephrase that. Would I be as warm as if I were on the other side of the window? So some heat gets through, but definitely not all of it. Would you agree with that?
Yeah.
So check it out. Greenhouse gases, in general, the greenhouse effect is caused by them. We're going to say that these are simply gases that allow light to pass through. But what doesn't?
The weaker light.
Weaker light, maybe.
The red ones.
I'm going to say not heat. Now, when we think of that idea of you wearing those black clothes, you obviously have to reflect some of the light. You don't absorb all of it unless you're wearing Vanta black, which you're probably going to pay more for that than you would wear outside anyway. Some of the light still reflects off you. I know that it does because I can see that Leanne is wearing black right now. It's absorbing some energy, but it's also shooting out a lot of energy at us. Okay, as we look at this, the heat doesn't get to leave. Once that energy is absorbed by our planet, it's stuck to our planet. It can't get back out through greenhouse gases. Now, greenhouse gases come from a variety of different things. Doesn't matter what they come from. As we're looking at it, I'm just going to show you my wonderful picture, and I'm going to leave it up to you. I will not ask you about specific percentages, just so you know. Like, I'm never going to ask you to memorize little pieces. So here's mine. As we look at light that's hitting the sun, or leaving the sun, again, not to scale. That is really pixely. Boom. That's a good picture. All right, check it out. Roughly 30% of the energy from the sun hits the outermost layers of our atmosphere and it bounces straight off. Okay, we have our upper layers here that do not let a ton of light through. Inevitably, is there some light that does get through? Yeah, like otherwise it'd be dark here all the time, right? Okay, roughly 70% of the energy that hits our planet is kept in the form of heat. So it strikes our planet and the ground warms up, the ocean warms up, whatever it is. Okay, 70% of the light. Now, once that's hot, anything hot radiates heat. Like if you've ever been to a sauna and felt coals, you know that they are radiating heat towards you. It's literally how we heat like all of our houses and stuff. Once this starts radiating all this 70% of light that's been caught by the planet, roughly 12% of it is able to expand or escape in our atmosphere. We know heat rises. It keeps rising. It's able to work its way out, which means if only 12% of the heat leaves, we get a bunch of it that winds up stuck, right? Now, if you check these percentages, there is something wonky about it. 12% of the heat goes to space. 57% of it gets trapped. We've lost some. Where do you think the other percentage went?
In the water.
Possibly in the water, but I'll tell you, water does a really good job of holding heat. Like water would be an awesome insulator if it weren't, for the fact that it's liquid. We're missing a bunch of percent. All this light has to pass through what? The atmosphere, and specifically like the stratosphere, there's a bunch of what that might catch a bunch of that energy? The ozone layer catches a bunch of it. Now, as we go out here, couple little things, and this is where we're going to pause for now. If we didn't have any atmosphere on our planet, which most planets have at least some semblance of an atmosphere, there isn't not an atmosphere on the moon. No atmosphere there. Okay, Earth would be significantly colder because we would lose all of our heat out to the vacuum of space. Luckily for us, it gets trapped. Otherwise, 33 degrees colder, life just wouldn't happen here. Okay, beyond that, in our atmosphere, a bunch of the important ones that we have, obviously, H2O. What's this G represent? Gaseous. This is steam, like just moisture in the air. What's CO2? Carbon dioxide. CH4? Cashening. Close. Methane, which, like, you'll hear this represented cow farts, whatever, like, for real. Not the only place it comes from, but that's a pretty common. And this is nitrous, like NOS that you've seen racing shows. Okay, these are all really important. Too much of a good thing is a bad thing, typically. Now, again, don't care where the too much comes from. Volcanoes erupt, those things happen. That's not the point here. Too much greenhouse gas, we get too hot. Too little, we get too cold. We are in the Goldilocks zone with where we're at right now. And there's a balance that the Earth naturally tries to keep up with. But maybe that's not super balanced right now, and it changes from time to time. Just throughout history, it keeps changing. It is changing. It's always changing. Now, from here, I think we're at a pretty natural stopping point.